Hi, I'm Bob. Let's finish the last 4 computer exercises today. For computer exercise 13, in part 1, we consider the unobserved effects model. What parameters can we estimate using first differencing? First differencing will eliminate all time constant variables, so we cannot estimate beta 0 and beta 1. We can use the xttab and xtsum commands to look at the information of the variables in the panel data context. We find that education does not change over time. Its within group variation is 0. In part 2, we estimate the equation from part 1 by first differencing and then do a test for the null hypothesis that the return to education has not changed over time. To do that, we first generate the interaction terms and the first difference terms using status for each command. It executes the commands inside the braces for each variable in the variable list. Next, we estimate the first difference equation and do an f-test for the joint significance of the interaction terms. The f statistic is 0.31 and its p-value is 0.95. It implies no change in the return to education over time. In part 3, we use the fully robust standard errors and do the f-test again. In Stata, we type the variance-covariance option and specify the cluster robust standard errors. The f statistic is larger, 1.00, and the p-value is 0.43. The interaction terms are still jointly insignificant at any reasonable level. Part 4 adds the interaction terms between year dummies and Julian. We estimate the model by first differencing. We use the same loop command in Stata to generate the interaction and the first difference terms. The estimated Julian wage differential in 1980 is the coefficient on the Julian variable, which is 0.106. It is statistically different from 0 at the 5% level. On average, the Julian members earned 10.6% more than the other workers in 1980, keeping education and other individual-specific and year-specific factors fixed. The Julian differential in 1987 is the sum of the two beta hats, minus 0.0415, but it is not statistically different from 0 at any conventional level. We can use the lincom command to obtain its standard error or employ the trick introduced in the textbook. In part 5, we test the null hypothesis that the Julian differential has not changed over time and discuss the results in light of your answer to part 4. The f statistic for the joint significance is 1.15 and its p-value is 0.33. The interaction terms are jointly insignificant. We could not reject the null hypothesis that the Julian differential has not changed over time. The Julian interaction terms, except for 1987, are individually insignificant at the 5% level. It is not surprising that they are jointly insignificant. Let's do computer exercise 14. In part 1, we estimate the simple regression model and report the results in the usual form. Based on this regression, does it appear that job training, which took place in 1976 and 1977, had a positive effect on real labor earnings in 1978? We regress real labor earnings in 1978 on the dummy variable job training. The simple regression gives a negative job training effect on real labor earnings. In part 2, we estimate the model by first differencing. It allows for individual fixed effects in the model. We generate the first differenced variables and then estimate the first differenced model. The intercept is for the coefficient on the year dummy, and the slope is for the training effect on earnings. Now it is positive and statistically significant. The workers who took part in job training earned $2,322 more than the other workers. We applied the first difference method to the two-period panel data. The unobserved fixed effects model accounts for the individual specific characteristics that correlate with the choice of job training. In the simple regression model in part 1, these factors are omitted from the model and cause a downward bias. In part 3, we will find the 95% confidence interval for the training effect using the usual OLS standard error and the heteroscedasticity robust standard error, and describe the findings. The 95% confidence interval using the usual standard error is from 0.731 to 3.922. The 95% confidence interval using the robust standard error is from 1.062 to 3.591. The latter is narrower because the robust standard error is smaller than the usual standard error for the job training variable in this case. Let's find answers to computer exercise 15. The dataset contains independently pooled cross-sections for the 7 years from 1994 through 2006, obtained from the General Social Survey. The dependent variable for this problem is a measure of happiness, VHappy, which is a binary variable equal to 1 if the person reports being very happy, as opposed to just pretty happy or not too happy. In part 1, which year has the largest number of observations? Which has the smallest? What is the percentage of people in the sample reporting they are very happy? In part 1, we can use the tabulate command followed by the year variable to find the number of observations for each year in the sample. There were 2,986 observations for 2006. That is the largest. 2004 has the smallest number of observations, 1,337. Out of 17,137 observations in the entire sample, 5,260 people reported they were very happy which is 30.69%. In part 2, we regress V happy on all of the year dummies, leaving out Y94 so that 1994 is the base year. Compute a heteroscedasticity robust statistic of the null hypothesis that the proportion of very happy people has not changed over time. What is the p-value of the test? We use the regress command with the variance-covariance matrix option to specify robust standard errors. The F statistic for the overall significance in the result window is 1.43. The p-value of the F test is 0.1988. We could not reject the null hypothesis that the proportion of very happy people has not changed over time at the 10% level. In part 3, we add 2 additional dummy variables to the model. Interpret their coefficients. How would we summarize the effects of church attendance on happiness? It is a linear probability model. The base group is those who never go to churches or only once a year. The coefficient on the dummy for those who occasionally go to churches is practically tiny and statistically insignificant. The coefficient on the dummy for those who regularly go to churches is 0.112. It implies that, compared to the base group, the people who regularly go to churches are 11.2 percentage points more likely to be very happy. In part 4, we define a variable, high income, equal to 1 if the family income is above $25,000. Include high income, unemployment, education, and teens in the regression in part 3. Is the coefficient on regularly attendant affected much? What about its statistical significance? We add the 4 explanatory variables to the linear probability model. The coefficient on the regular church attendance variable does not change much. We can compare the estimates in the table. The statistical significance does not differ much either. In part 5, we will discuss the size, magnitudes, and statistical significance of the 4 new variables in part 4. Do the estimates make sense? They all make sense. The high-income people's probability of being very happy is 3 percentage points higher than low-income people. The unemployed people are 9.8 percentage points less very happy than employed people. 1 more year of education is estimated to increase the probability of being very happy by 1 percentage point. The above 3 explanatory explanatory variables are statistically significant. The number of teenagers in the household does not significantly affect happiness. In the last part, controlling for the factors in Part 4, do there appear to be differences in happiness by gender or race? Justify your answer. We can add gender and race variables to the model and find the significance. In this case, we add the female and the black dummy variables. From the t-statistics, we find that happiness does not differ by gender, but it significantly differs between black and non-black people. Black people are 6.6 percentage points less very happy than non-black people, holding all the variables in the model fixed and accounting for the year fixed effects captured by the year dummies. Now we reach the last computer exercise, number 16, for chapter 13. The dataset covers murders and executions for 2,197 counties in the United States. In Part 1, we will find the average value of the murder rate across all counties and years. What is the standard deviation? For what percentage of the sample is the murder rate equal to 0? We use the summarize command to find the sample average and standard deviation, which are 0.508 and 0.851 respectively. We find that 15,651 observations have a 0 murder rate. That is 41.9% of all observations in the entire sample. In Part 2, we will answer how many observations have an execution equal to 0. What is the maximum value of execution? Why is the average execution so small? We use the count command again and find 37,144 observations have an execution equal to 0. We use the summarize command to find the sample average and maximum value. The sample average is 0.0069 and the maximum value is 7. The sample average is so small because 37,144 out of the 37,349 observations have a 0 value. In Part 3, we consider the model. What do we need to assume about the county fixed effects AI and the execution variables in order for pooled OLS to consistently estimate the parameters? We need to assume that the county fixed effects AI is not correlated with the execution variable for all time periods. In Part 4, we apply OLS to the equation from the last part and report the estimates of beta 1 and beta 2 along with the usual pooled OLS standard errors. Do you estimate that executions have a deterrent effect on murders? We can use the by sort prefix to generate the first leg of the execution variable within each county. Then we estimate the model by pooled OLS. Since the model contains a different intercept for each time period, we use the I dot in front of the categorical variable year to specify dummies for each year. The estimate for beta 1 is 0.176 and its usual standard error is 0.041. The estimate for beta 2 is 0.137 and its usual standard error is 0.043. Because the coefficients are positive and significant, we do not find a deterrent effect of executions on murders. We are familiar with the reason now. The model suffers from omitted variable bias. Although the model has the race, gender, and age composition as the control variables, there could be some county-specific unobserved factors in the county fixed effects AI, and these unobserved factors are very likely correlated with the choice of execution in that county. One such unobserved factor could be the residents' attitude towards the law. In Part 5, we are asked whether the standard errors attained from Part 4 are valid. No, the usual standard errors are not valid because the homoscedasticity assumption is not satisfied. To see that, we can do the BP test. We use the predict command in Stata to obtain the residuals and then square the residuals. From the regression of the squared residuals on all the explanatory variables, we find that the F statistic for the overall significance is 6.84 and its p-value is 0 to 4 decimal places. We reject the null hypothesis of homoscedasticity of the error term and conclude that the original model is subject to heteroscedasticity. The usual standard errors are not valid as a result. In Part 6, we estimate the equation in Part 3 using first differencing to remove AI. What are the new estimates of beta 1 and beta 2? Are they very different from the estimates from Part 4? We use the D operator in front of the variables to get the first difference. The estimates for beta 1 and beta 2 from the first difference equation are negative now, although not statistically significant. After controlling for the county-specific unobserved factors by the fixed effects, the estimates have the expected signs. For the last part, we cannot say there is evidence of a statistically significant deterrent effect of capital punishment on the murder rate. Using the cluster in county standard errors to evaluate the serial correlation and heteroscedasticity, the estimates for beta 1 and beta 2 are still statistically insignificant. Thank you so much for doing the computer exercises with me. Please subscribe to my YouTube channel if it helps. See you in the next chapter. Thank you for watching this video and subscribing to my YouTube channel. See you next time.